about 10 times at least, and drink about 20 protein shakes a day. That was vodka. Okay, today, we're going to talk about also what I like to do. It's called work. You know what the integral force? You see, force is measured in newtons. We do that over a certain distance, meters, you get a joule. Work, measured in joules. And that's the story.
Today, Cody Lane is going to show you how to bench press.
Yeah, I know. It's me again. Right now, I'm exerting some force on this bar. You know, I'm benching it because it's got a weight of about so many newtons, and I'm exerting the force over a certain distance while I bench it.
Roar! Come on, Cody, let's go!
Roar! Took him to church. I like bleach, man. Why you have the stupidest verses? Got everybody giving them guest spots.
Roar! Come on, Cody, let's go! Roar!
20% skill, 15%
Yeah! Alright, this is the Great American Race. Are you ready for this? 3, 2, 1, go! Winner!
Hi, folks, let's face it, we need a solid understanding about calculus. And that takes work. So, I'm gonna teach you about work. That's very useful because you work like every day, bro.
Work is a force in the direction of motion times displacement. It can be modeled simply by the equation W equals Fd, where W stands for work, F stands for force, and D represents the displacement through which the force is applied. This means there has to be displacement for work to be done. Let's say there's a couch, and Nathan wants to move the couch. And he tries so hard. But no matter how hard he tries, he can't move it. There was no displacement, so no work was done on the couch. Now let's say there's a house, and Nathan wants to run around the house. So he does. And once he completely runs around the house, he finishes exactly where he started. Even though he's exhausted, he didn't do any work, which is kind of depressing. Now, there's another problem. The equation W equals Fd can only be used if a constant force is applied. In many situations, a constant force is not present, except when working against gravity, for example. If the force, f of x, is not constant, work is found by taking the definite integral of force from an initial position A to final position B. W equals the integral of f of x evaluated from A to B. Now let's look to the example of Cody Lane bench pressing. Because of Cody Lane's immense muscle mass, he was bench pressing 50 pounds. Let's make all of our measurements in SI units, just to make our answer have units of work in joules. So first, we must convert pounds into kilograms, and we do that by dividing 50 by 2.2, and the result is a mass of 22.727 kilograms. To find the force in newtons, we use the equation F sub g equals mg, where F sub g is the force of gravity, m is the mass, and g is the acceleration due to gravity, which is 9.8 meters per second squared. So after multiplying 9.8 times 22.727, we end up with a force of 222.727 newtons, which is the amount of force both of Cody's arms were exerting. Because Cody's arms returned to his original position after each cycle of bench pressing, this would mean his net work is 0. So we are going to find out how much work he does on only pushing the bar from his chest until the point when his arms are fully extended. The distance from his chest to his arm fully extended is 0.71 meters. This will give us the limits of integration as his initial position, x sub I equals A, which equals 0 meters, and his final position, x sub F, equals B, which equals 0.71 meters. Now it's time to take the integral of force. Cody exerted 222.727 newtons of force from 0 meters to 0.71 meters. W equals the integral from 0 to 0.71 of 222.727 dx. Now we anti-derive it to get 222.727x evaluated from 0 to 0.71, which equals 222.727 times 0.71 minus 222.727 times 0, which when multiplied out equals 158.136 minus 0, giving us a final answer of 158.136 joules of work. This is the amount of work Cody did in pushing the bar up. So, springs are kind of fun. You can do lots of fun things with springs. You can stretch them and stuff. Now, springs have a different kind of force when you stretch them. They have a tension force. See, we can use other forms of force, such as tension in a spring, to find work as well. Most springs follow something we call Hooke's law, which states that force, F, equals negative kx, where k is the spring's force constant and x is the distance the spring is stretched. So let's say a spring, which is at equilibrium position, which is its unstretched state, is 13.5 inches long. When a 45-pound weight is hung from its spring, it stretches to a length of 14 inches. Using Hooke's law, we can find the spring's force constant. The 45 pounds is the force F exerted, which equals k times x. X is given by the distance it was stretched, so we take the difference between its final position and its equilibrium position, which is 14 minus 13.5. We get an x value of 0.5 inches. So plugging that into the equation, we get the k value to equal 90. Now, by knowing this, we can find the work done on the spring by any force applied to it. Let's say our same spring was at equilibrium again and you pulled it to a length of 16 inches. How much work did you do on the spring when stretching it? Since work is the integral of force, and force in this case equals F equals kx, we must take the integral of kx from our initial position, which is 0 because it was at equilibrium, to our final position, which is 2.5 because it was stretched. We know that work equals the integral of kx from 0 to 2.5 dx. We can move 90 to the outside because we know it is a constant. Next, we anti-derive this. Once we do that, we get 90 times 1/2 kx squared evaluated from 0 to 2.5. Now we plug in the limits of integration for values of x, and we get 1/2 times 2.5 squared minus 1/2 times 0 squared, all multiplied by 90. After we simplify this more, we get 90 times the quantity of 3.125 minus 0, which is 90 times 3.125. We multiply that through to get work equaling 281.25 joules, which is the amount of work done on the spring. Okay, bye.